Hello and welcome to another CasaFrog from Inside the Box. Today we have a wonderful Yokogawa 6.5 digit bench multimeter that we would like to have performing automated test and response on our measurement network. These meters were typically provided with either an RS-232 or GPIB interface for integration, well before the time where Ethernet was included for free and an open API existed for inclusion on the marketing flyer. Ours happens to have RS-232. These images from the Yokogawa manual indicate that the serial interface and the GPIB interface use the same command format, which simplifies our efforts in control later. We could use a USB to RS-232 adapter, a bunch of cables, and perhaps a small dedicated PC as a bridge. However, that tends to get messy quickly. Preferably, we would like this to be standalone and directly connect to our measurement LAN. An ESP32 would work well here, however, I prefer to have the devices hardwired when possible. To that end, a variant of the ESP32 dev boards exists under the ETH01 model, and in this case, one by wirelesstag.com is the choice. It includes the PHY requirements for Ethernet onboard and still leaves plenty of I/O pins for other purposes. It's time to get under the hood and try not to lose any of those precious ppms. I'm pretty sure a couple are going to get out here. Maybe even through the hole we have to cut in the back sheet metal. This fits, and in fact it's a very nice location. It's right next to the communications board with that wide 1.5-inch ribbon sitting there. I think I'll be making a bracket for it anyways. But this ribbon goes underneath to the other side. Here we go, let's get it flipped over to the master communications board, and on here, yes, it looks like a couple serial converter chips. Given the age of this machine, I was actually expecting some MC 1488s and 89s. However, this one has LinearTech's LT 1081s on it. Not a bad chip. In fact, it has both serial transmit and receive level shifting in one single package, which is quite handy as opposed to the 88s and 89s. Okay, yeah, dual in the package actually. Not so bad. So to this end, time to start some tracing. I'm not quite convinced there's a symmetry here, so let's look at the RS-232 pinout from scratch. So this is a DB25, and we're interested in pins 2, 3, and 7. We don't need any handshaking, so we'll just pop that back in here. And I also want to find a logic 5 for power. Just want to confirm that that's here, which thankfully it is. And since I have the Rigol turned on, I'm just going to use it as opposed to getting out another multimeter, aside from the one that's on the bench that we're currently servicing. So we got a good 5 volts there, happy with that. And it's time to start tracing non-return zeros. And with RS-232 serial, NRZ is a typical response, especially on TTL level shifters. And honestly, it didn't match up here. So either the RS-232 is going across both chips, or there's transmit and receive going across both chips for RS-232 and GPIB separated out. There's an amount of time that I could spend, reverse engineering this, but easiest is actually just to feed it some data. So I have our serial monitor just sending some known data, and we're just trying to pick up the traces coming in here. I would really prefer to just run TTL level out of the ESP32 and pop it directly into the communications receiver here, but honestly this isn't looking right. Every time I drop a different impedance onto that line, it's a little bit okay, and then it falls out. I have a feeling what we're going to have to do is actually put our own level shifter ahead of this and tie into the DB25 itself. So I have a small 9-pin to TTL guy there. We're just going to tie it on and level shift our level shifting. It's a little over the top, but it's definitely something that is a lot more reliable. I could pull the original Yokogawa's level shifter chips out there and desolder them. I'd rather not. We'll leave them alone. And as you can clearly not see me bodging some wires on here, would never bodge wires directly onto the side of an IC. That would be absolute hypocrisy. We'd never do that. So that's why you can't see this here. Definitely not happening. Not bodging wires onto the side of an IC. But for the sake of comments, let's just pretend there was a magic footprint that was unused that said install remote RS-232 connections here. Yeah, that'll work. So we had an RX and a TX lines, and time for some soldering. Let's get this put together. This is not going to be an ESP32 coding tutorial by any means. As an overview, we do need the WTO1 Ethernet libraries. We'll skip the Wi-Fi since it's supposed to be hardwired. We will include an MQTT pub/sub broker. Serial 2 will be used for communicating with our device meter. The CMD topic will simply pass through. An auto response will follow every CMD request, and we'll be on the lookout for conflicting string variable types, especially when it comes to being able to break apart the raw display response for our later convenience. Once a basic framework is written, such as serial testing and basic attachment to an MQTT server on our local LAN, we can start to see what is needed to bridge what the meter wants to receive in regards to its command protocol, what responses it returns, as well as how we want the data formatted on our end. Since this is going to an MQTT server, we could very easily just forward raw commands and return raw responses. I would like a little extra here. Although our data manager, in this case OpenHAB, can tear apart the text string from the meter, I would prefer that we get it in a usable format at the MQTT level, which means taking that cryptic string of code, value, and exponent, and performing some string tricks. The hardware serial ports here really do prefer the Arduino string class, and yes, that's string with a capital S. I can already hear the comments blowing up for how evil the string class is, and everything should be and only handled with character arrays, which for embedded is quite appropriate. However, unless you are to write all your own libraries and never deviate from the Espressif IDF kernel, you will inevitably run into situations where one library uses one variable type and another uses the opposite. Converting the strings, with a capital S, to C strings, or char arrays, can get one into trouble. Converting the other way can get into even more trouble. This is a situation here. In fact, further on in the OpenHAB integration, we get some conversion errors where there are too many different variable types. Do make sure to check out the video on OpenHAB and FluxDBD Grafana MQTT as a metrology controller. In that I show the setup of Debian Linux container system from bare metal all the way through receiving and cataloging data for Grafana dashboards. There are plenty of videos describing this process on the internet. However, this one is a speed launch with a design for disaster recovery and doesn't even include turning on a single light switch. This is a very straightforward bridge application. It has listeners which subscribe to specific MQTT topics, in this case the command topic, and will take the command as presented and forward it unmolested directly to the meter. There are no error checks, there are no filters. The meter handles this already, since you could of course send it whatever text you wanted across RS-232 or GPIB. Upon the execution of a process command, we have a mandatory display return function. This is an additional command sent to the meter to return its current display data. Although we could send this command via MQTT, there isn't an automated bridging of the data that way. By performing the display command separately, we can also add a timer routine to periodically send data to the MQTT topic without an external source even making the request. This is handy for data logging over a long period. When this meter gets integrated to OpenHAB, this capability means we don't have to write any sequences. Simply attach the leads, set the mode, and walk away. Each state change will get logged to the InfluxDBD measurements, and it becomes actionable data for whatever testing we are doing. By tradition now, I always include startup confidence information in topics as well, and this application is no different. The MQTT topics are defined as CMD for incoming commands, data for outgoing information, which is given as a combination of raw and split with the mode and float values separated. A state topic reveals status information such as the IP address of the device, its identifier, the last command, the meter status register, and some other convenience variables, since we don't actually have a screen on our ESP32 device. This particular meter, based upon the documentation in the manufacturer's manual, has a known line termination. In this case, it's simply new line, which makes it easy to pull the incoming serial data as the response from the meter and simply wait for the new line character to terminate the loop. That unfortunately does make it a blocking function. However, we can overload that with a timeout for safety. For our application, since it is a loop of recurring information, it is likely better for a data element to die and disappear rather than get logged as corrupted. At the end of the day, small deviations can of course be filtered out. However, the fewer, the easier that process becomes. I'm using the utility MQTT Explorer, which I really like because it is incredibly simple, but has a few features beyond just a command line utility. The graphing panels are very convenient, however you need to have interpretable numbers for it to work. This is the reason why I want to have both the raw display response and the numeric value extrapolated. At this point in the development, I do have an MQTT server being connected by the ESP32, but no other automation. MQTT Explorer doesn't have any type of persistence, so when you close the application, your graphs and historic go away. However, for testing, this is perfect. Even before going into trials, I knew a second revision was necessary. I'm a firm believer in functional first, sexy second. First off, I hated the string type conversion inconsistencies, probably more than you did. Thus, I converted everything to be a default Arduino string type, and then used the C-stir method for anything that wanted C-type character arrays. This choice was not taken lightly. It actually took printing out the code and tallying which methods wanted what type and determining the most effective refactoring path. In the end, Arduino strings won out as the default, and the code is appropriately much cleaner. Additionally, I also created a lot of statically typed variables in the first version, so scaling to other devices would be difficult. Once the string types were taken care of, rewriting to have variables in the server host name, device identifier, auto reply timer, and some others was easier. Saving that to EEPROM-based parameters was also a beneficial convenience. Finally, I wanted to also write these parameters remotely, so a JSON blob inside the state topic will indicate the current bridge configuration, and writing that same string with updates to the config topic will permit the bridge to be updated. Ah, data points. Beautiful, beautiful data points. And all without having to parse a single CSV file or handwritten notes. That's all for now. Thanks for watching, and we'll see you in the next video.